So we saw in the last set of lectures segments, we looked at dimensional analysis and the Buckingham pi method for ways of coming up with a pi parameter, which are non-dimensional groups that are important for collapsing data within experiments and experimental fluid mechanics. What we're going to do now is we're going to spend a little bit more time looking at some of the most common dimensionless groups. Now, the Buckingham pi method enabled us to come up with dimensionless groups without knowing a lot about the system that we're looking at. We can go through other techniques of coming up with these non-dimensional groups. For example, if you take the Navier-Stokes equations and go through a non-dimensionalization procedure, and what I'll do, I'll outline how you would non-dimensionalize the different terms in the Navier-Stokes equations. So if you were to take the Navier-Stokes equations and make substitutions for velocities, length scales, time, and pressure, and replace everything with the star terms, we would end up with an equation that looks something like this. So this would be our total or substantial derivative. We would have a gradient of pressure, plus we would have our viscous dissipation term, and it would be multiplied by some pre-multiplier here. So we've transformed the Navier-Stokes equations into this new equation, but what we notice is that we have this pre-multiplier term here, and what this is it's 1 over a very common non-dimensional number in fluid mechanics, the Reynolds number. And so by going through this process, this gives another example that there are other mechanisms or ways that we can get these non-dimensional parameters that are very, very important within fluid mechanics. So that is another technique that we can obtain these parameters. Now, the physical significance of the dimensionless groups, let's take a little bit of time looking at that. So if we look at a lot of the non-dimensional numbers that are important to fluid mechanics, it turns out that there are ratios of forces in the fluids. And so we're going to look here at 6 different types of forces, and then we'll look at a number of ratios and the resulting very well-known non-dimensional numbers that result. Okay, so these are some of the forces that are involved in fluid mechanics. We have the inertia force, that is rho v squared times L. Viscous force, we find it's the viscosity times velocity times some characteristic length scale L. Pressure force is a pressure differential multiplied by an area, so we get delta PL squared. Gravity force is mass times gravity, which works out to be density times some length scale cubed times gravity. Surface tension would be the surface tension coefficient multiplied by some length L. And finally, the compressibility force is the bulk modulus multiplied by some area. And so what we're now going to do, we're going to form ratios of some of these different forces. And we'll find that when you do that, some very, very well-known non-dimensional numbers drop out. So we're going to begin with the Reynolds number. And it turns out that the Reynolds number is a ratio of inertia forces to viscous forces. And so if we perform the ratio using those forces, we get rho vd over mu. And this is a number that is used to classify the state that the flow is in. And typically, as a rule of thumb, a low Reynolds number, although low is relative, it depends upon the type of flow that you're looking at, be it flow over a cylinder, a sphere, a flat plate, because there the characteristic dimension will change. But typically, if it's a low Reynolds number for the application, the flow would be laminar. And if it's a higher Reynolds number, it could be turbulent. And between the two, you go through a transition zone. But again, these numbers, exactly what does low and what does high mean depends upon the nature of the flow field that you're looking at. So that is the Reynolds number. Another one is the Euler number, although quite often it's referred to as being the pressure coefficient. And this is the ratio of pressure forces to inertia. So Euler number EU, although I never use that and very rare that I see it, it's often represented as being the pressure coefficient C sub P, and that would be our delta P divided by, and we introduce a 1/2 rho V squared. And the thing in the denominator, well, first of all, CP is the pressure coefficient. And that can be expressed often as P minus P infinity divided by 1/2 rho V infinity squared. Now, the term in the denominator here, this is often referred to as being dynamic pressure. And it is sometimes given the symbol Q infinity. And the other term in here, P infinity, that is pressure free stream, or free stream static pressure. And then P in this equation obviously would be the pressure that is of interest at some given point in the flow field. So that is the pressure coefficient. And a lot of this derives from Bernoulli's equation. If you recall, at a stagnation point, we had V equals 0, and with that, Bernoulli's equation, if you're following a streamline, so let's assume 1 is the stagnation point. With that, we can say P1 is P naught for the stagnation pressure. V1 is equal to 0, and with that, we get on the left-hand side is P0, and on the right-hand side, we have P infinity plus 1/2 rho V infinity squared. And this here is our total pressure. And then we have the static. And then we see also the term that is in the denominator of our pressure coefficient, that is the dynamic pressure. And so if you're wondering where we get that 1/2, it's coming out of Bernoulli's equation, and it just makes it easier when we do the scaling. So that's where this here is the Q infinity that we saw in the previous slide. Here, when we look at our pressure coefficient, we have dynamic pressure in the denominator, and it's coming out of Bernoulli's equation. So that is the pressure coefficient. Other non-dimensional numbers that we have non-dimensional numbers that are related to wave activity, and the Freud number is the one that we use. And this is a ratio of inertia to gravity. And if we write the Freud numbers squared and we look at the ratio of these terms, we get something like this, which then collapses down to something like this.